Estimating electrical loads for commercial and industrial facilities is crucial for ensuring safety, reliability, and efficiency. The National Electrical Code, or NEC, provides guidelines and requirements for these calculations. For commercial buildings, such as IT companies or data centers, several factors must be considered. Firstly, lighting loads are a significant component. The IES Lighting Handbook offers detailed methods for calculating lighting loads based on the specific requirements of different commercial spaces. Secondly, receptacle loads, which include general-purpose outlets for computers and other equipment, must be estimated. NEC Article 220.14 provides guidelines for calculating these loads, typically based on volt-ampere per square foot. Thirdly, heating, ventilation, and air conditioning, or HVAC, loads can be substantial, especially in data centers with cooling requirements. These loads should be calculated based on the equipment's nameplate ratings and any applicable diversity factors. Fourthly, data processing equipment loads, specific to IT companies, need to be accurately assessed. NEC Article 645 provides additional requirements for data processing systems. Fifthly, demand factors, as specified in NEC Article 220, can be applied to reduce the calculated load based on the likelihood of simultaneous operation of different loads. Several resources can assist in estimating commercial electrical loads. Estimating commercial building electrical loads discusses factors to consider and methods for calculating these loads. NEC Chapter 9 provides tables and formulas for calculating load currents in commercial buildings. For industrial facilities like cement plants, sugar refineries, and oil refineries, the electrical load calculation process involves similar but also distinct considerations. Firstly, motor loads are often the dominant factor in industrial settings. NEC Article 430 provides detailed requirements for calculating motor loads, including locked rotor current and overload protection. Secondly, process equipment loads, which vary depending on the specific industrial process, must be carefully evaluated. This may involve consulting equipment manufacturers' specifications and considering any applicable duty cycles. Thirdly, transformer loads, which supply power to various equipment and systems, need to be accurately calculated. NEC Article 450 provides requirements for transformer protection and sizing. Fourthly, lighting loads in industrial facilities may differ from those in commercial buildings, often requiring high-intensity lighting for safety and productivity. Fifthly, safety factors are especially important in industrial load calculations to account for potential future expansion and unforeseen loads. Estimating electrical loads for industrial applications discusses specific considerations for industrial electrical load calculation, including motor loads, process loads, and safety factors. NEC Chapter 6 provides tables and formulas for calculating loads for specific industrial equipment, such as motors and transformers. The NEC provides specific guidance on calculating loads for various types of equipment. For example, NEC Article 220 covers branch circuit, feeder, and service calculations, including general lighting loads, small appliance and laundry branch circuits, appliance loads, and motor loads. NEC Article 430 provides detailed requirements for calculating motor branch circuit, feeder, and overload protection. NEC Article 440 covers air conditioning and refrigeration equipment. NEC Article 450 provides requirements for transformers. NEC Article 625 addresses electric vehicle charging systems. The NEC also includes tables for determining conductor ampacity and allowable voltage drop. NEC Table 310.15b16 provides ampacity ratings for insulated conductors. NEC Informative Annex C provides guidance on voltage drop calculations. To accurately estimate electrical loads, it's essential to gather detailed information about the equipment and systems that will be connected to the electrical system. This includes nameplate ratings, operating characteristics, and duty cycles. Consulting with equipment manufacturers and experienced electrical engineers can also be valuable. Additionally, considering future expansion and changes in technology is crucial to ensure that the electrical system has sufficient capacity. Overestimating loads slightly can provide a buffer for future growth and prevent costly upgrades later. It's also important to regularly review and update load calculations as equipment is added or replaced. Using specialized software and tools can streamline the load calculation process and improve accuracy. Several electrical design software packages offer features for load calculation, voltage drop analysis, and short-circuit studies. These tools can automate many of the manual calculations and help identify potential issues. In addition to the NEC, other standards and guidelines may be applicable depending on the specific application and location. These may include local built-in codes, energy efficiency standards, and industry-specific standards. Consulting with local authorities and industry experts can help ensure compliance with all applicable requirements. For example, Leadership in Energy and Environmental Design, or LEED, standards may apply to commercial buildings seeking certification for energy efficiency. Compliance with these standards can affect the electrical load calculation and system design. Also, Occupational Safety and Health Administration, or OSHA, regulations may apply to industrial facilities requiring specific safety measures and equipment. Furthermore, NEC Article 110 covers general requirements for electrical installations, including working space around electrical equipment, guarding of live parts, and identification of disconnecting means. Understanding and complying with these requirements is essential for ensuring a safe and reliable electrical system. In summary, accurate electrical load calculation is critical for both commercial and industrial facilities. By following the guidelines and requirements of the NEC, considering all relevant factors, and utilizing appropriate resources, it's possible to design electrical systems that are safe, reliable, and efficient. Remember to consider lighting, receptacle, HVAC, and data processing equipment for commercial buildings, while motor loads, process equipment, and transformer loads are vital for industrial facilities. Applying demand factors and safety factors appropriately can optimize the design and prevent overspending. Regularly review and update load calculations, and utilize software tools to improve accuracy. Finally, comply with all applicable standards and regulations to ensure a safe and code-compliant installation. One of the key aspects of electrical load calculation is understanding the concept of demand factors. Demand factors are used to reduce the calculated load based on the assumption that not all loads will be operating at their maximum capacity simultaneously. The NEC provides tables of demand factors for various types of loads, and these can be applied to the calculated load to determine the minimum required capacity of the electrical system. It is important to note that demand factors should be applied judiciously and only when there is a reasonable basis for assuming that the loads will not be operating at their maximum capacity simultaneously. Overly aggressive application of demand factors can result in an undersized electrical system that is unable to meet the actual demand. Another important consideration in electrical load calculation is the impact of harmonics. Harmonics are distortions of the sinusoidal waveform of the electrical current, and they can be caused by nonlinear loads such as electronic equipment, variable frequency drives, and uninterruptible power supplies. Harmonics can cause a variety of problems in electrical systems, including increased heating, reduced power factor, and equipment malfunction. It is important to consider the potential impact of harmonics when calculating electrical loads, and to take steps to mitigate their effects, such as using harmonic filters or specifying equipment that is designed to minimize harmonic generation. Power factor correction is another important aspect of electrical load calculation. Power factor is a measure of how effectively electrical power is being used. A low power factor indicates that a significant portion of the electrical current is not being used to do useful work, but is instead circulating in the electrical system and causing increased losses. Power factor correction involves adding capacitors to the electrical system to offset the inductive reactance of the loads, thereby improving the power factor. Improving the power factor can reduce the amount of current that is required to supply a given load, which can reduce energy costs and improve the capacity of the electrical system. Voltage drop is another important consideration in electrical load calculation. Voltage drop is the reduction in voltage that occurs as electrical current flows through a conductor. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC specifies maximum allowable voltage drops for various types of circuits, and it is important to ensure that the voltage drop in a circuit does not exceed these limits. Voltage drop can be minimized by using larger conductors, reducing the length of the circuit, or increasing the voltage of the circuit. Short circuit studies are an important part of electrical system design. A short circuit study is an analysis of the electrical system to determine the magnitude of the fault currents that would flow in the event of a short circuit. This information is used to select protective devices, such as circuit breakers and fuses, that are capable of safely interrupting the fault current. A short circuit study also helps to ensure that the electrical equipment is adequately rated to withstand the mechanical and thermal stresses that would be caused by a short circuit. Grounding is a critical aspect of electrical safety. Grounding involves connecting the non-current carrying metal parts of electrical equipment to ground, which provides a low impedance path for fault currents to flow back to the source. This helps to ensure that protective devices will operate quickly and safely in the event of a ground fault. The NEC specifies detailed requirements for grounding electrical systems, and it is important to follow these requirements carefully to ensure the safety of personnel and equipment. Surge protection is another important consideration in electrical system design. Surges are transient overvoltages that can damage or destroy electrical equipment. Surges can be caused by lightning strikes, switching operations, or other disturbances on the electrical system. Surge protection devices are used to protect electrical equipment from surges by diverting the surge current to ground. The NEC provides guidance on the selection and installation of surge protection devices. Emergency power systems are required in many types of buildings to provide power to critical loads in the event of a power outage. Emergency power systems typically consist of a generator and automatic transfer switch. The generator is sized to supply the critical loads, and the automatic transfer switch automatically switches the loads from a normal power source to the generator in the event of a power outage. The NEC provides detailed requirements for emergency power systems. Renewable energy systems, such as solar photovoltaic or PV and wind power systems, are becoming increasingly common. These systems generate electricity from renewable sources and can reduce reliance on fossil fuels. The NEC provides specific requirements for the installation of renewable energy systems. Energy efficiency is an important consideration in all electrical system designs. Energy-efficient equipment and lighting can reduce energy consumption and lower operating costs. The NEC and other codes and standards provide guidance on energy-efficient design practices. Commissioning is the process of verifying that an electrical system is installed and operating in accordance with the design specifications. Commissioning helps to ensure that the system is performing as intended and that any problems are identified and corrected before the system is put into service. Maintenance is essential for ensuring the continued safe and reliable operation of an electrical system. Regular maintenance should include inspections, testing, and cleaning of electrical equipment. The NEC and other standards provide guidance on electrical system maintenance. Documentation is an important part of electrical system management. Accurate and up-to-date documentation should include drawings, specifications, operating manuals, and maintenance records. This documentation is essential for troubleshooting problems, making repairs, and planning future upgrades. Safety is the most important consideration in all electrical work. Electrical work should only be performed by qualified and experienced personnel. All electrical work should be performed in accordance with the NEC and other applicable codes and standards. Personal protective equipment should be used to protect workers from electrical hazards. The National Fire Protection Association, or NFPA, 70E standard provides guidance on electrical safety in the workplace. By following these guidelines, you can create accurate and reliable electrical load calculation for any commercial or industrial facility, ensuring safety, efficiency, and compliance with applicable codes and standards.